Madison College Building Construction for the Fire Service, Week 4, Homework Problem 6. In this problem, you'll be using moments and forces to determine basically a series of forces at the supports of this diving board. So, as is stated in the problem, this person has a weight acting downward of negative 160 pounds. And again, the negative is just by convention. It's a downward force, so we label it with a negative magnitude. The diving board itself weighs 140 pounds, but because it's uniformly distributed, we consider it to act at the center of the board. So if you think about the center of this board, the total board is 12 feet. There's 6 feet on this side from the end to this center point, and then 6 feet over here as well. And that force at the center is the entire weight of the board, 140 pounds. And that's something that you'll see repeatedly in engineering, is that we try to make things act as though they act at a single point, that all the mass of the board is concentrated in one location. And again, it's a negative number, negative 140 pounds. Now let's see what it's asking. Calculate the vertical forces acting on each support A and B. Include the directions of the forces. So you could solve this problem a couple of ways, but basically you have to treat this thing as though one of these is hinged and the other is simply a support or in tension. And I'm going to choose, in this case, to make point A the hinge. So I'm going to say that this is supported, this is free to hinge about point A, and a reaction at point B counteracts the moments such that this thing stays in static equilibrium. So let's set up the problem the way we set up every one of these. The sum of the forces in the x directions, well, I don't see any x arrows in here. I don't see any forces left or right, so that is just simply 0. The sum of the forces in the y direction, well, we've got the swimmer's weight, which is negative 160, and we've got the board's weight, which is negative 140. And then we have the forces developed at A and B. And we don't know what those are yet. Those are what we're trying to solve for. And the force at B. And of course, what these all need to add to, that negative 160 plus the negative 140 plus the force developed at A plus the force developed at B, all need to add to 0. Let's think for a minute about the sum of the moments. So I'll come down here. This will be a little bit longer. I'll give myself a little more room to write it out. The sum of the moments equal, well, the moment generated by the swimmer, which, I don't know, I guess I'll call it M sub S, the moment generated by the swimmer, is the swimmer's weight times the swimmer's distance. So 160 pounds times 13 feet. And again, this will be a negative number because it's producing a clockwise rotation. So 160, and that's a negative number, times 12 feet. It's negative 1,920. Now, I don't know why I wrote a label in there. Let's get rid of that label and just write the value in. So I don't really need a label there. And again, the numbers are negative 1,920 foot-pounds. Okay? Now, the moment generated by the board itself is that negative 140 pounds times the distance of 6 feet. So again, it will be a negative number. So 140 negative times 6 feet is a negative 840 foot-pound moment. Now, if this is going to be in static equilibrium, there has to be some other counteracting positive moment that will be equal to each of these. And that's going to be the moment created by this upward push by support B. So just this far into the analysis, we know that the column B is going to be under tension. So I will call this force B. And there's a moment that's created by force B, and it's equal to force B times the distance from the pivot to point B, which is 4 feet. So I don't know the total moment, but I know that it's or I should say I don't know the force, but I know that it is 4 feet times whatever force is developed at B. Well, we can push this around a little bit to get force B by itself, and let's think about how we would do that. We would say force B equals, and I'm going to divide both sides by 4 so that force B is by itself, divided by 4 feet. And then I'm going to take these other two negative moments and I'm going to add them to the other side. 1920 plus 840 divided by 4. That's going to tell me the force acting at point B. It's going to tell me the amount of compression, the compression force in that column B. So we'll clear out of this. And these are positive numbers now because we've moved them onto the other side of the equal sign. 1920 plus 840 is 2760, and we're going to divide that by 4. And we find that the force, the upward force at point B is 690 pounds. Now, there are a number of other ways that we could figure out the force at A, but here's perhaps one of the easiest. We know that all of the forces in the y direction have to add to 0. Well, let's think about what we know so far. We know we have a negative 160, that's the diver's weight, and a negative 140, that's the board's weight, and an upward push at column B of 690 pounds. It's a positive number because it's upward, plus the force at column A. That all has to add to 0. Well, now we just simply push all of this other stuff to the other side of the equation and we'll be able to determine what force A is. Now, maybe the easiest thing is let's just do this sum and just push one number onto the other side of the formula. Okay, so we'll get out of here. 690 pounds, positive, minus 160, minus 140 is 390 pounds. So we could rewrite this as 390 pounds plus force A equals 0. Well, how do you get force A by itself? You subtract 390 pounds from both sides. So force A equals negative 390 pounds. Now, what does that mean? Well, you could think of column A as pulling downward with a force of 390 pounds. That would be one way to be thinking about this, is that force B is pushing upward with a force of 690 pounds. Force A is pulling downward with a force of 390 pounds, and if we add all of the y components together, we find out that we get 0. Another way to think of it is that you could imagine that point B acts as the pivot. The board is pulling up on column A with 390 pounds, and you could think about a negative upward force in tension. Two negatives make a positive. This can be useful to us. For instance, if you were to try to chop this thing down, which of these supports would you cut with the chainsaw? Well, column B here is under compression. If you attempt to cut this with the chainsaw, the kerf is going to collapse and pinch the bar on the saw and you're going to be stopped. On the other hand, if you cut column A is under tension, which means the kerf, which is the gap that's created by the saw as it makes the cut, is going to expand as you go, and so you're not going to get the saw stuck. Of course, another thing to be thinking about is if you're standing down here, when you cut this thing's going to develop a strong negative moment. This whole thing is going to roll in the clockwise direction about point B, which means this end's going to come up, and if you weren't prepared for it, you might take it right in the chin. So the moral of the story here is that with some really simple analysis, you can figure out forces that are going on inside a structure, both in terms of magnitude, which isn't particularly important on the fire ground, but also in terms of direction or quality, in other words, tension or compression. And that may be of some use in making tactical decisions.